This print is supposed to be a print that represents a binary put. The value of a binary put is as a function of what the stock is worth and how much time is left until expiry. What's a binary put? Well, take a look at this ticket. The ticket says that the person who has this, who owns this ticket, is entitled to get $1 if the stock expires less than $10. So say the stock is going to expire in a week. If it expires in a week at less than a $10 price, then you can trade this ticket in for $1. If it expires at greater than $10, then the ticket's not worth anything. What should you pay for this ticket now? Well, the most it can ever be worth is $1, and the least it can ever be worth is $0. So your answer is probably going to be some sort of weighted average between $1 and $0. And your answer would depend then, the weights, I guess, the weights between $1 and $0 would probably depend on what the stock is trading at now. If the stock is trading at, I don't know, $1,000, then you're going to think, yeah, the chance that the stock's going to drop below 10 and make this ticket worth something, pretty slim. So your weights will be more towards the 0 and less towards the 1. Whereas if the stock is trading at $1, you can probably think, well, most likely it's going to finish less than $10. It might go up a bit, but I'll still finish less than $10. And this ticket I have, this option, this derivative on the stock, will be worth $1. So I should pay somewhere closer to $1 for it. In fact, if the stock was $0, if the stock was trading at $0, you'd say, company's out of business, stock is going to finish at $0. That means this ticket is going to be worth $1, so I should pay, well, a little bit less than $1 because of time value of money. So our argument is that this binary put should be worth something in between $0 and $1. It should be a weighted average of those two outcomes, of the two possible payoffs, and that weighted average should be discounted for time value of money. And we've already argued that its value should be a function of what the current stock price is. It should also be a function of the time left until expiry. If we said that the stock was trading at $20 and there was only a day left, it's probably going to finish at greater than $10, so this thing is probably going to pay off 0, so my weights would be closer to weighting the 0 heavy and weighting the 1 less. Or if I said, okay, the stock's trading at $20, but there's like a half a year left until expiry. Now you'll say, yeah, half a year, that's a long time. The stock could fall less than $10, or at least there's more of a chance of it falling less than $10 and your binary put finishing in the money than in the scenario we said when there was only a week left. So it should also be a function of the time left until expiry. The value of this option depends on the stock. Its value is derived from the stock. That's why we call it a derivative. This binary put option, its value should be a function of the time left until expiry and the value of the stock. Let's graph that for a particular time. Here's a plot. The value of the option as a function of what the stock price is, and there's about a month left until expiry. So if the stock price is low, you're probably going to get $1, so the price is closer to $1. If the stock price is high, past the exercise price, past the $10, some people call it a strike price, then your value of it is weighted closer to the 0 amount. And as time goes on, we see that the two extremes are coming closer and closer. As time goes on, we can see that that the value is approaching the value curve is approaching the payoff function. Now the payoff function of a binary is just, it's 1 until you hit $10 and then it's 0 after. So there's the payoff function, 1, 0. The stock is 0 here, the stock is 20 here. And we can see then, well, I guess you have to look at it this way. The stock is 0 here, the stock is 20. And as time goes on, the surface, the slice with respect to time is morphing into the end here, which is the payoff function. Now you're looking at it backwards. But time is going this way, stock value is going this way. The function that we're graphing, the actual function that we're graphing, is a solution to the Black-Scholes partial differential equation with that particular digital payoff of 1 and then 0 after 10. So here's the Black-Scholes partial differential equation. The solution to that Black-Scholes partial differential equation for any particular payoff is given by this formula. So we have to solve this formula. We'll get a function. The function that we get is a function of both the stock value and the time until expiry. That gives me the height for the particular S, t value. Interestingly enough, when we derive that Black-Scholes equation and then solve that Black-Scholes equation for any particular payoff, we make a lot of assumptions, and they're all assumptions that we know are not quite right. So remember, when you're looking at this surface, this is assuming that the stock is moving at a log normal fashion. The returns are, the log of the returns are normally distributed. We know that's not exactly true. It has fat tails, but we say close enough. We also assume that there's no arbitrage opportunities, but of course they are. People make a lot of money exploiting these arbitrage opportunities. Anyway, there's a whole list of assumptions. Those are the sort of the two major ones that we do assume. We know they're not exactly right, but we use this solution to price those. We use that solution to plot the price of this binary put as a function of the stock and time.